We'll be ready to start. Let me start by just welcoming everyone to this first lecture of our June workshop for the Simons collaboration on special holonomy in geometry, analysis, and physics. And we're pleased to have our first lecturer is Dominic Joyce, who will speak on universal structures in enumerative invariant theories. And I think I got the title more or less right. So Dominic, take it away.
Thank you. Is that, are you now seeing my slides?
I am, yes.
Good. So I want to talk about, well, so this is joint work with Jacob Gross and Yuji Tanyaka. Whoops. You can see it's on the archive in a paper a few weeks ago. And we're talking about different kinds of counting invariants. So like Donaldson invariants of four manifolds, or Donaldson-Thomas invariants of Calabi-Yau threefolds, Fano threefolds, invariants counting sheaves on surfaces, that kind of thing. And the idea is that we want to find some sort of universal structure underlying many of these things. Just if we can take ourselves back to the instant days of January, here is the last slide of my talk in January. And at the time, Robert and Mark told me sadly that it wasn't going to be possible to hold our conferences in a way which did much less flying. And now here we are. So let me just say, when all of this is over, let's not go back to doing everything we did before. Anyway, so
Dominic, I want to say, be careful what you wish for.
Yep. Yes, whoever thinks that one person can't change the world has not eaten an undercooked bat. Anyway, so what I want to talk about today is enumerative invariants in both algebraic geometry and differential geometry. And these are the study of invariants which count objects E in some problem, in some category of adjective objects, let's say, under some sort of stability condition. Sometimes the notion of stability is more or less hidden in the problem, but it's there. And we're going to count objects E, such as coherent sheaves or representations of some algebra, or maybe instantons on a four manifold, with fixed topological invariants. The class of V is going to be alpha. These are really the something like the Chern character of your sheaf, perhaps. Usually this counting is done by means of some kind of a virtual class. For the moduli space of semi-stable objects, and the virtual class is taking value in some homology theory, in the homology of a moduli space. And then if you want to get actual numbers, then you integrate over this homology class, you integrate some natural cohomology classes, mu alpha, to get this. So I'm thinking, for example, of Simon's polynomial invariants of four manifolds. So I'm going to call the theory C-linear if the objects E you count live in a C-linear additive category. So additive means we've got a nice notion of direct sum, for example. So that would hold for things like vector bundles, maybe with connections, or coherent sheaves, or representations of something. C-linear means that the morphisms between the objects in the category are complex vector spaces. So for example, one of the most interesting cases of this is Mochizuki style invariants counting coherent sheaves on compact complex surfaces. We can think about these as sort of algebraic Donaldson invariants of four manifolds, where the four manifold is a complex surface. You might want to think about Donaldson-Thomas invariants counting coherent sheaves on a Calabi-Yau threefold or a Fano threefold. As I'm sure I've told you before, there is a notion of Donaldson-Thomas type invariants for Calabi-Yau fourfolds using a slightly different notion of virtual class which is kind of connected to the problem of counting spin 7 instantons. And finally, Gauss invariants of 4 manifolds. I'd like to think about these in particular with the structure group U of M for all M. And in order to fit into the framework I'm going to talk about today, we ought really to restrict to the 4 manifolds with B2 plus equals 1, because then we have wall crossing phenomena for the Gauss invariants. Okay, so I conjecture that lots of theories of this kind share a common universal structure. So I'm going to give you an outline of this structure, which is going to take 3 slides, I think. So firstly, I'm going to work in the world of stacks, and I'm going to form 2 moduli stacks, M and MPL of all objects E and A. So M is the usual moduli stack, which is what you just write down if you're being an algebraic geometer. MPL is what I call the projective linear moduli stack, which parameterizes objects E modulo not isomorphisms, but projective isomorphisms. So what I mean by projective isomorphism is a family of isomorphisms divided out by the group GM or U1, we quotient out by multiples of the identity. So this changes the notion of isomorphism objects. It changes the moduli stack you get. Secondly, I want to be given a quotient of the, well, so if K0 of A is the Grothendieck group of all objects in your category, quite often that may be very big, too big. So K of A is a quotient of that. It's a lattice of topological invariants of E. For example, K of A may be the lattice of Chern classes, and this map from the K theory of the category to maybe the Chern class, the Chern character map, let's say. And then we can split M as a direct sum of stacks M alpha over all alpha in this K of A group. A good choice for K of A is usually the numerical Grothendieck group. And MPL also splits into a disjoint union of pieces. So then we also suppose there is a symmetric biadditive Euler form, chi, going from K of A cross K of A into Z, which is often used to compute the dimension of the moduli spaces. So we can form the homology of stacks, or moduli spaces more generally, over the rationals. The homology of M is a direct sum over all alpha of the homology of M alpha, and the same thing for the projective linear stack. So these are graded by the usual grading in homology. It turns out that we want to shift the gradings by a certain amount, and we shift the component H star of M alpha by minus chi alpha alpha for the ordinary moduli stack M, and we shift it by 2 minus chi alpha alpha for the projective linear moduli stack. So I'm going to have homology with a hat on the ordinary moduli stack, homology with a check on for the projective linear moduli stack, and these are both shifted versions of the homology with these 2 different shifts. Okay, so in work I've talked about a couple of times before in these conferences, I think, we can make the shifted homology of the ordinary moduli stack into a graded vertex algebra, and the shifted homology of the projective linear map into a graded Lie algebra. Okay, so the vertex algebras aren't going to play much of a part of this story. What we're mostly going to care about is this Lie algebra structure. The Lie algebra structure kind of comes from the vertex algebra, but if you don't know what vertex algebras are, then today you needn't worry about it. Okay. So fifthly, I want a notion of stability condition Tor on my category A. So if A is coherent sheaves on some smooth projective variety, usually the nicest notion of stability is Giesecke stability for some polarization, ample line bundle on X. If we're doing gauge theory, for example, if we want to do Donaldson theory for a compact oriented four manifold X with B2 plus equals 1, then the correct analog of stability condition is the splitting of the second de Rham cohomology group into H2 plus and H2 minus, induced by fixing a Riemannian metric G, and then taking these to be the vector spaces of harmonic self-dual two forms and harmonic anti-self-dual two forms. So it's well known that Donaldson invariants in the B2 plus equals 1 case undergo wall-crossing behavior as this splitting of the second de Rham cohomology group changes. And we'd like to think about this as a stability condition. If you want to see why that's kind of analogous to the coherent sheaf case, note that Giesecke stability is really induced by a choice of Kähler form. And when B2 plus equals 1, this H2 plus of X is a one-dimensional thing and is essentially spanned by a self-dual two form omega you think about as a Kähler form on your four manifold. Okay, so once we have a notion of stability condition, then for each alpha in our K theory, we can form moduli spaces, a stable moduli space and a semi-stable moduli space of Tor semi-stable or Tor stable objects in class alpha. Well, the stable moduli space is a substack of the projective linear moduli stack. And in the cases we're interested in, we can give it some kind of structure of a virtual oriented manifold. So, I mean, it's in some sense, it's quite close to being a manifold. In algebraic geometry, your notion of virtual oriented manifold might be a C-scheme with a perfect obstruction theory in the sense of invariant and Fantacci. In differential geometry, if you make a genericness assumption on the metric you use to define your instance on moduli space, for example, then you may well find that your stable moduli space is actually an oriented manifold in the usual sense. So the stable moduli space has this nice property of having this virtual structure. The semi-stable moduli space, under good conditions, will be compact or proper in algebraic geometry. So therefore, if the stable moduli space equals the semi-stable moduli space, so if there's no strictly semi-stable objects, then you have a compact virtual oriented manifold, which has a virtual class. A homology class, well, it might be in the homology of the moduli space itself, but we regard it as an element of the homology of the projective linear moduli stack MPL alpha. Okay, so the virtual dimension of this should be 2 minus chi of alpha alpha, where the 2 is really the GMs which we divided out by to form the projective linear moduli stack in the first place. And this 2 minus chi alpha alpha was the shift in which we used to define this shifted homology. So therefore, this virtual class lives in the shifted zero homology of the projective linear moduli stack, which we've already said has the structure of a Lie algebra. Okay, so far there aren't any conjectures. We can prove all of A through to E already in the cases we care about. So let me now move on to the conjectural part of the picture. So for many theories of enumerative invariants, there is a problem in defining the invariants, the virtual class of a semi-stable moduli space in the case in which the stable moduli space is not equal to the semi-stable moduli space. Oops. So that is when the moduli spaces M, SS alpha of Tor contain strictly Tor semi-stable points. In gauge theory, so in Donaldson theory, for example, you should interpret the strictly semi-stable points as being reducible connections. So the reason for the problem is that then that we want to use some kind of a virtual, what I call the virtual manifold structure. For example, a invariant Fantacci obstruction theory, or maybe just even the structure of a smooth manifold on a moduli space. Typically, when you pass to at the strictly semi-stable points, this virtual manifold structure breaks down. So you can no longer define your Fantaxi obstruction theory, or you might find that your instanton moduli space has singularities which might look, for example, like a cone on CP2 or something like that. So it's a well-known problem defining the invariants in the case in which you have strictly semistables. So one of the main things we say is that we conjecture that there is a systematic way to define virtual classes for counting strictly semistables in homology over the rationals, not over the integers in these cases. So in gauge theory, this counting process should require a condition analogous to B2 plus greater than equal to 1. So, as is well known, for a four manifold with B2 plus equals 0, you have problems with defining the invariants because of reducible connections, and I'm not saying we have anything to help with those problems. Okay, so firstly, I claim we can define invariants counting strictly semistables for all classes in our K theory, not just for those in which there are no strictly semistables. And secondly, if you have two different stability conditions, let's call them Tor and Tor twiddle, and some alpha in your K theory, I expect that there is a universal wall crossing formula. You can write the invariants for one stability condition, Tor twiddle, let's say, in terms of the invariants for the second stability condition, Tor, by this general formula. So this is a sum of repeated Lie brackets. I'm taking the Lie bracket of the alpha 1 invariant with the alpha 2 invariant, and I'm taking the Lie bracket of that with the alpha 3 invariant, and so on. So if I've got n invariants, I have to take n minus 1 repeated Lie brackets. And these are multiplied by some combinatorial coefficients, u twiddle, depending upon the topological invariants and the two stability conditions. And these constants are defined in my previous works on wall crossing formulae for Motivic invariants. And this Lie bracket here is the Lie bracket on this shifted zero homology of the projective linear moduli stack, which came out of the vertex algebra picture, which I talked about before. Okay, so, and then the third part of the conjectural picture is that, well, as I said, initially I'm just claiming that there exist interesting classes counting strictly semistables without really telling you where they come from. But it's often possible to give an explicit inductive definition of these invariants counting semistables, including strictly semistables, using this wall crossing formula 1 in an auxiliary abelian category and the method of pair invariants. So this is a method I used in my work with Yino and Song on Donaldson-Thomas invariants, also used by Mochizuki in his work on counting coherent sheaves on surfaces, and by various other people. Okay, so in the archive paper, we prove our conjectures in probably the simplest case, which is that the abelian category A is the category of representations of a quiver Q without oriented cycles. So this condition of without oriented cycles is needed to make the moduli spaces compact so that the virtual classes are well defined. And with the stability conditions, we take to be slope stability. So in this case, by work of Alistair King, if the stable moduli space equals the semi-stable moduli space, then the semi-stable moduli space is a smooth projective scheme. So it's smooth because we're looking for it without relations. And it's thus a compact complex manifold given by a GIT quotient of just some affine space or vector space by a group which is, well, a projective. It's a projective group of a product of general linear groups. So therefore it has a fundamental class as a compact complex manifold. And we, if there's no semi-stables, we set the virtual class just to be this fundamental class. But we can also give a definition of this virtual class in the case in which the stables is not equal to the semi-stables, and therefore this moduli space is not a complex manifold. Okay, so, well, I know how to extend the proof from quivers to quivers with relations and slope stability using Fantacci virtual cycles, and also to a full Calabi-Yau version of quivers called DG quivers, with the kind of virtual cycle used in my work with Borisov on Johnson-Thomas type invariants of Calabi-Yau fourfolds. So these are kind of toy models for more interesting categories such as coherent sheaves on various bases. So I believe that I'm quite close to being able to prove the conjectures for categories of coherent sheaves on X, when X is a curve or a complex surface or a Fano threefold, using Giesecke stability and Fantacci virtual cycles. Now, if that proof worked, then a similar method should also work for Calabi-Yau fourfolds, provided Borisov-Joyce virtual cycles behave well under torus localization. And Richard Thomas has promised me that the proof of that is coming. So hopefully work of Richard Thomas and Korean postdoc O should enable me to finish the job. For now, I don't have anything sensible to say about Donaldson theory or any other gauge theory problem. Okay, so let me make a few remarks about various things. Firstly, about counting strictly semi-stables. So in the case in which the stable moduli space equals a semi-stable moduli space, the virtual classes are defined by using some geometric structure on this semi-stable moduli space. For example, it could be a smooth C-scheme, or a C-scheme with perfect destruction theory, or it might be a -2 shift epileptic derived scheme. And this is using a known construction, for example, the Berendt-Fantacci or Lee-Tian virtual cycles. So, well, okay, this may not be quite true now. When I wrote the slides, if the stable moduli space is not equal to the semi-stable moduli space, then we don't really have a definition of this virtual class in terms of a geometric structure on the semi-stable moduli scheme or stack itself. Although I now have some hopes of doing this via using geometric invariant theory. So for quivers, our proof works by showing that there are unique classes when stables not equal to semi-stables, which extend the classes you have when stables equal semi-stables, and which also satisfy the wall crossing formula for virtual cycles under chain of stability condition. So therefore, in some sense, the definition I'm giving for these virtual cycles actually involves all possible stability conditions, not just one. And in the Calabi-Yau threefold case, for the Donaldson-Thomas invariants defined by myself and Yinan Song, and also the Kontsevich-Soderman version of the same thing, counting strictly semi-stables is a complicated problem. And you have to use rational weights which depend upon the decomposition of your strictly semi-stables into stable factors by Jordan-Holder filtrations. Okay, another kind of comment. So there's a notion of Motivic invariant in algebraic geometry. So an invariant I of x, let's say of algebraic varieties over some field K, x, taking values in some commutative ring R, is called Motivic if it's additive under being cut up into pieces. So that's if y is contained in x as some closed subvariety, we want I of x to be I of y plus I of x take away y. And also it should be behave nicely under products. So some examples of Motivic invariants are the Euler characteristic, with the ring being the integers, virtual Poincare polynomials, virtual Hodge polynomials, and so on. Okay, so some time ago, I worked I developed a big theory of semi-stable invariants accounting moduli stacks of stable or semi-stable objects using Motivic invariants, and this theory included a wall crossing formula and a change of stability condition. An important tool in this was the use of Ringel-Hall algebras and Ringel-Hall algebras of things I call stack functions, ff of m on moduli spaces m. Broadly, these are some kind of generalization of constructible function. And you can see papers by me titled Configurations on Abelian Categories 1 to 4, and then following that, the work on Donaldson-Thomas theory of Calabi-Yau threefolds. Okay, so the homology of our moduli stack, H star of m, virtual classes in homology are not motivic, because motivic things are always somehow local. You can see, you know what the contribution of every point in your in the thing you're counting is to the overall or invariant. Whereas homology classes are kind of non-local, they live on the entire space. So we can't use this old work on motivic invariants to study virtual classes. However, and in fact, you can, it's quite easy to prove that forming virtual classes requires your moduli space to be compact. And this process of cutting something into two pieces has to destroy the virtual class. It's just impossible for virtual classes of Baron-Pantechi type to fit into this framework. But the new theory I'm telling you about, it works by taking the old theory, the old results about invariants and wall crossing formulae, which were set in a Lie algebra of stack functions. And then we just replace this Lie algebra of stack functions by this Lie algebra of homology classes that comes out of my vertex algebra work. So I'm really plugging together two big theories. I'm plugging together the work on motivic invariants and wall crossing formulae from the early 2000s with this vertex algebra and Lie algebra work on homology moduli spaces to get this new picture. Okay, so we can ask which invariant theories fit into our framework. So I expect the following to work. Firstly, counting vector bundles or coherent sheaves on projective curves, X. Counting sheaves plus extra data, Higgs fields or whatever, on curves. Counting sheaves on surfaces with H20 of X equals 0, following Mochizuki's Springer lecture notes volume. Donaldson-Thomas invariants of Fano threefolds. Donaldson-Thomas type invariants of Calabi-Yau fourfolds. And on the gauge theory side, U of M Donaldson invariants of four manifolds with B2 plus equals 1. Also various algebraic problems such as counting representations of quivers, quivers of relations, Calabi-Yau 4, e.g. quivers, and so on. Some obvious things you can ask about with firstly Donaldson-Thomas invariants of Calabi-Yau threefolds. Well, they're kind of related, but they don't fit into exactly the structure above. Partly because I said I wanted the virtual dimension of the moduli spaces to be 2 minus chi of alpha alpha. And in the Calabi-Yau threefold, the virtual dimension is actually minus chi of alpha alpha, where chi of alpha alpha is 0. In the Calabi-Yau 3 case, we don't have this dimension shift by 2, which kind of screws up the whole picture a bit. Similar comments apply for Donaldson invariants with B2 plus is greater than 1, and for counting sheaves on surfaces H20 of X is greater than 0. So actually, if you just applied our theory naively, it would work in these cases too. But then the invariants are automatically 0 because the B2 plus greater than 1 or the H20 greater than 0 contributes obstructions to the obstruction theories of your moduli spaces, which cause the invariants to be 0. If you want to get non-zero invariants, then you have to fix determinants. And then that changes the character of the story. I presume that there'll be some kind of generalization of our story to the B2 plus greater than 1 case, but I'm not sure yet what it says. Okay, so let me ask a few interesting questions and future projects. Firstly, do the invariants in all of these theories have some kind of common universal structure determined by a small amount of data? So the thing I have in mind is something like Donaldson invariants for manifolds being written in terms of Cyber-Witten invariants, or the MNOP conjecture writing certain families of Calabi-Yau threefold Donaldson-Thomas invariants in terms of Kronov-Witten invariants and so on. Secondly, can we do anything with this vertex algebra structure? Because the vertex algebra structure is just sitting there on the homology moduli stack and doesn't really get used for anything other than to produce a Lie algebra on the homology of different moduli stack, which is then how you write the wall crossing formula for invariance under change in stability condition. But I feel that the vertex algebra structure ought to have some use. It ought somehow be related to deep properties of enumerative invariance, such as modularity of generating functions and so on. Another question, how should we modify our picture to include theories like Donaldson theory for B2 plus is greater than 1, or surfaces H2 0 of x is greater than 0? And the reason I haven't taken this very far yet is because in these cases there's no wall crossing of invariance. So there's not an obvious theorem to prove. However, counting strictly semistables and the pair invariant story still makes sense. So we should probably at least be able to say, give a coherent way of defining invariance in the cases in which there are strictly semistables or reducibles. We could ask about replacing homology by some complex-oriented generalized homology theory, such as K-theory or K-homology. So enumerative invariants in K-theory are already studied in various places, and I'd like to see whether that fits into a nice picture. So the vertex algebra story does generalize to K-theory in a nice way. So we could ask about extension to triangulated categories and bridges and stability, and we could ask whether our picture has an interpretation in string theory. Okay, so now let me go back to the beginning and explain things in a bit more detail. I'm going to explain the algebraic geometry version of the theory only. So let's take A to be a C-linear abelian or triangulated category from algebraic geometry. So we could work with the coherent sheaves on a smooth projective scheme or its derived category. Or we could, for example, take the category of representations of a quiver or its derived category. So we write M for the moduli stack of objects in our category A. This is an R-trans stack in the abelian category case. It's what's called a higher C stack in the triangulated category case. There's a morphism phi going from M cross M into M, which acts as a direct sum. The multiplicative group GM, this could be U1 in the K-theory case, this acts on objects E in A by constant multiples of the identity. And this induces a morphism, well, a stack morphism from the stack point mod GM cross M into M of the group stack point mod GM on M. So this theory is very stacky. You need to develop some intuition for what stacks do to follow it, really. And then the projective linear moduli stack is a quotient of M by this group stack here. We're really factoring out all of the multiples of the identity in the automorphism groups of the objects. And there's a morphism M over MPL, which is a fibration with phi on point mod GM over M take away 0. Okay. So we need some extra data. Firstly, a quotient of the K-theory of A, giving you these splittings of the moduli stacks into pieces with fixed topological invariants, a symmetric biety of Euler form, as I said before. More interesting piece of data is a perfect complex theta on M cross M, satisfying a bunch of assumptions, including that the rank of theta on M alpha cross M beta is chi of alpha beta. So theta determines chi alpha beta. So there's really going to be two interesting cases for this invariant story. Either in the Four-Calabi-Yau case, we take theta to be the dual of the Ext complex, where this is a complex computing Ext groups between objects in our abelian categories. And this choice of theta goes along with using Borisov-Joyce virtual classes. The other possibility is to take theta to be the direct sum of the Ext complex, the dual of the Ext complex, and the swapped around Ext complex, where sigma swaps around the two factors M. And this is for use in the case in which we're going to use Behrens-Fantecchi virtual cycles. Okay, so we need some signs epsilon alpha beta which compare orientations on M alpha, M beta, and M alpha plus beta, but we won't worry about that. So with this data, so this is all the extra data we need to make homology into a graded vertex algebra with the shift I talked about before. Explicitly, this formula gives you the vertex algebra structure. The main piece of the vertex algebra structure is what's called the state field correspondence, y of u comma z. So if u and v are homology classes, then this rather complicated formula tells you what the vertex algebra is. The identity is the identity in H0 of M0, which is usually just a point. And okay, so then the vertex algebra story makes all of this into vertex algebras and Lie algebras. Okay, so it's worth noting that you can often write down the homology, or the shifted homology of these two spaces rather explicitly. And somewhat surprisingly, the answer is usually simpler if you're working with derived categories. So for example, my student Jacob Gross proved that if you have a smooth projective C-scheme X is a curve or a surface or a toric variety or one of several other categories of things, and M is a moduli stack of objects in the derived category of coherent sheaves, then the shifted homology of M is, well, it's, you take the symmetric algebra on the even K theory, tensored by t squared q of t squared. This is just a kind of infinite thing. And the exterior algebra on the odd K theory, tensored by that. And then you tensor it with the group algebra of semi-topological K theory. So this is the topological K theory of the complex manifold. This, you can think about it, if you like, as a kind of K theory of type P, comma P, or something like that. And so that's a very explicit presentation of your homology of your moduli stack, provided you can compute the K theory of your manifold, which is usually relatively straightforward. The vertex algebra structure is also entirely explicit. It's what's called a superlattice vertex algebra, based on the superlattice of essentially even plus odd K theory. So we can actually use this for explicit computations in examples, as well as for abstract theory, because once we have a very explicit description of this homology, then we can give formulae for what our virtual cycles look like in the kind of coordinates given by this. So even if you only care about the abelian category of coherent sheaves, then it makes sense to work in this derived category moduli space, because so you can use this explicit presentation of it. And although Lie algebras are much simpler objects than vertex algebras, it turns out to be rather difficult to write down the Lie bracket on the projective linear moduli stacks homology explicitly. And actually the best way appears to be go via the vertex algebra structure on this first. And that was how I actually invented this in the first place. I was trying to write down a Lie bracket on the homology of this moduli stack, and I ended up essentially inventing the vortex definition of vertex algebras on this thing as a kind of tool. And that, in fact, was how vertex algebras were originally invented, as they cropped up when you were trying to understand Cox-Moody algebras and their representations. Okay, so next let me talk about virtual classes of moduli spaces. So the vertex algebra and Lie algebra story I've talked about so far actually works very, very generally for moduli stacks of objects in of coherent sheaves when X is a smooth projective scheme of any dimension. But defining virtual classes, and therefore actually having an enumerative invariant theory with nice properties such as deformation invariance or whatever, is much more restrictive. Typically, it restricts you to low dimensions. So if your category A has dimension 1, that is, if it has X, only X0 and X1, but no higher X, for example, representation of quivers or coherent sheaves on the curve, then the moduli stacks are actually smooth. So moduli, if stable equals semi-stable, the moduli stacks of semi-stable objects is a smooth projective scheme, and therefore has a fundamental class just as a compact complex manifold. If the dimension of the category is 2, for example, quivers with relations or coherent sheaves on surfaces, then what you get is a projective scheme with a perfect obstruction theory. And Invariant tell you how to define a virtual class in the Chow homology of that moduli scheme. There are then 3 special cases: coherent sheaves on X a Calabi-Yau threefold or a Fano threefold. You can define Invariant virtual classes for, as Richard Thomas showed us. I'm going to have to throw out the Calabi-Yau threefold case later. And then finally, coherent sheaves on Calabi-Yau fourfolds. Myself and Dennis Borisov defined a different kind of virtual class. And this is really a different kind of category to these first 3, because the Borisov-Joyce virtual classes have half the expected dimension of the virtual classes in the other cases. Okay. Next, let me say that there's 2 main ways of forming moduli spaces in algebraic geometry. You can use schemes or you can use stacks. And I guess most algebraic geometers prefer schemes. One important difference between these is that if you have a moduli stack of objects E, then the automorphism groups of the objects are recorded in the isotropy groups of your stack. So a stack has a richer geometric structure, including essentially a Lie group of the complex numbers at each point, called the isotropy group. So the isotropy group of M at an isomorphism class E is the automorphism group of the schemes E. But when you take a moduli scheme, the scheme forgets the automorphism groups. So our moduli stack M and MPL, they have the same points, but they differ in their isotropy groups. The isotropy group of M at E is the automorphism group of E, but the isotropy group of MPL at E is the automorphism groups divided by the multiples of identity. Now, if E is a stable object, then properties of stability conditions imply that the auto of E is just GM. So therefore, the isotropy group of the projective linear moduli stack of E at the point E is 1. So therefore, it looks like a scheme and not a stack. So schemes are very nearly stacks with trivial isotropy groups, though algebraic spaces really should be what you should be talking about. But anyway, therefore, the Tor stable moduli scheme is actually an open substack in the projective linear moduli stack, but not in the ordinary moduli stack. So that's the thing which makes the projective linear moduli stack useful for these counting invariants. Okay, so the Tor stable moduli scheme has a good property of living inside the projective linear moduli stack. The semi-stable moduli scheme, under good conditions, has a nice property that it's usually compact or proper. But it has a bad property. Firstly, that it doesn't map to the MPL or to M. And secondly, the obstruction theory, or whatever other nice structure you've got on the stable moduli scheme, generally doesn't extend to the semi-stable moduli scheme. So therefore, we can't define a virtual class unless the stable moduli scheme equals the semi-stable moduli scheme. Okay, so let me now sketch how we prove our conjectures in the case of quivers. So let's take Q to be a finite quiver. So Q0 is a set of vertices, Q1 is a set of edges, and H and T are maps from Q1 to Q0, telling you the head and the tail of each edge. Then we have a C-linear abelian category on CQ of representations of V. So these representation of Q gives you a finite dimensional vector space, big V little v for each vertex, and a linear map rho e for each edge. The dimension vector of a representation is d in n to the Q0, where d of v is dimension of the vector space at the vertex. And then we can work out our theory very explicitly in this case. So the moduli stacks are of the form M is the disjoint union over D in n to the Q0 of MD, where MD is a quotient stack, the quotient of a vector space, RD, direct sum of HOMs, and then GLD is the product of general linear groups of dimensions of the components of the dimension vector. PGLD is GLD divided by the GM, which lies is the multiples of the identity in all of the general linear groups. Because RD is a vector space, it's contractible, so it doesn't change the homology. The homology of MD is the homology of BGLD. Homology of MPLD is the homology of BPLGD, which you can write down explicitly using calculations of Miller and Starr, Sitchev, and so on homology of classifying spaces. Okay, we have a notion of slope stability on quiver categories, which I won't talk about too much. So you get slope stability, and under slope stability, the notions of stable and semi-stable correspond to GIT stability or GIT semi-stability for our appropriate linearization of the action of your PGLD on the vector space RD. So therefore, our moduli schemes are GIT stable or semi-stable quotients, like that. And if Q has no oriented cycles, then one of the GM subgroups of PLG acts on RD with all positive weights, and that's enough to ensure that the semi-stable moduli is actually an objective C scheme, so it's compact. Okay. So therefore, sorry. Okay. If Q has no oriented cycles, and mu is a slope function on what's CQ, with space equals the semi-stable moduli space, then the semi-stable moduli space is a smooth projective scheme, has an open substack of the MPL, and it has a fundamental class. It has dimension 2 minus chi of dd, where chi is this formula here. Okay, so our first theorem is that if Q is a quiver with no oriented cycles, then for all slope functions, mu on mod CQ and all dimension vectors, there are unique classes M vert in H2 minus chi of dd of this projective linear moduli stack, which is the shifted zero thing, with two properties. Firstly, if there are no strictly semi-stables, then this virtual class is just a fundamental class of the smooth projective scheme. And secondly, these invariants transform according to the wall crossing formula I gave you a while ago in the Lie algebra under change of stability condition. Let's see if I can find that. So this formula here, it prescribes the virtual class for one stability condition in terms of the virtual classes for a second stability condition, repeatedly brackets, and some combinatorial coefficients, which are relatively easy to write down. Okay, so that's our first theorem. We also prove a second theorem. There is a notion of a morphism of quivers, lambda going from Q into Q primed. An example of a morphism of quiver would be deletion of some edges of some quiver, for example. But there are also more complicated morphisms. This notion of morphism induces a functor between quiver categories, and also induces morphisms of the vertex algebras and of the Lie algebras. And it turns out that if mu prime is a slope function on the target category, you can pull it back to a slope function on the domain category, and the virtual classes satisfy the push forward of the mu virtual classes is equal to the mu prime virtual classes together with some factorial things. So, okay, I'm not sure what you're supposed to get out of that, but it seems interesting that these enumerative invariants have some kind of functoriality under functors between categories, and the morphisms of vertex algebras we're defining here, they're not it's not the obvious thing. We're not just mapping one moduli stack into the other. We're also capping with the top Chern class of some vector bundles and things like that. Okay, so here's how we go about proving these theorems. I call the slope function mu decreasing if for all directed edges in Q, the real numbers mu v and mu w used to define the slope function satisfy mu v is greater than mu w. So the slopes decrease in the direction of the edges. So such decreasing slope functions exist if and only if Q has no oriented cycles. And if you've got a decreasing function, then it turns out that, well, for each dimension vector, either D is 1 at some vertex and 0 elsewhere. In that case, the moduli space is just 1 point. Or it's n at some vertex and 0 elsewhere, where n is greater than 1. In that case, well, the stable moduli space is empty, the semi-stable moduli space is a point mod G, P, G, L, N, C, and the virtual dimension is negative. Well, finally, D is not one of these cases, and the moduli spaces are empty. So because of this, for a decreasing slope function, the counting invariants are entirely determined. They have to be 1 in the homology of this thing, which is just a point for delta V, and 0 otherwise, because in case B, the homology class has to live in the negative homology of this moduli stack, which is of course 0. Okay, so there are some slope functions, decreasing slope functions, for which the invariants are entirely determined. So therefore, if we take some fixed decreasing slope function mu, the previous equation, and the wall crossing formula from mu to mu prime to determine unique classes for all slope functions. Therefore, if these classes, there's only one possible choice of these virtual classes, provided the theorem's true. So we prove that this defines classes satisfying theorem 1 part 2 for wall crossing from between two different stability conditions, using an associativity property of the wall crossing formula, which I proved a long time ago. And then we have to prove that these classes satisfy part 1 of the theorem, which is that if stable equals semi-stable, then the virtual cycles are the fundamental class. That's quite complicated. And okay, well, never mind. Let's move on. Okay, so the most difficult part is to show that these things satisfy the theorem part 1i, which is the virtual class equals fundamental class, and in a special case we deduce this using the Joyce Song results on Donaldson Thomas type invariants of quivers, and then we kind of build up to progressively more general quivers and dimension vectors by using this morphism of things in different ways. Okay, so these methods are really very special to quivers, but I'm working at the moment on extending to other categories, particularly coherent sheaves, and I've got 3 methods. Firstly, comparing the category you're interested in with the category of representation of quivers, and then deducing the conjecture from the theorem for quivers. So, for example, there's a paper by Alvarez, Consul, and King, which, roughly speaking, gives you a functor from coherent sheaves on X into moduli into the category of quiver representations for a Kronecker quiver, provided you're happy to restrict to a kind of bounded piece of curve X. And then you can kind of pull back the invariance here to invariance there. Secondly, one can use methods in Mochizuki's work on invariance counting coherent sheaves on surfaces involving Graeber-Pandey GM localization and enhanced master spaces. And I've got a third approach, which involves wall crossing in GIT quotients. And Geoffrey Kieran residues, which doesn't seem to require master spaces. Okay, so anyway, that's all I've got. Thank you.
Let's see, we have some time for questions, a little time for questions and discussion. Are there questions for, I think all of you except the co-hosts are able to raise your hands if you want to ask questions.
Let me do that.
I think there should be under, if you bring up the participants.
Yeah, Richard, I think, has raised his hand. Richard Thomas.
Richard Thomas has his hand raised. You can see the blue. Right, there you go. Dominic?
Hi, Dominic. Maybe this question isn't valid because you ruled out the Calabi-Yau 3 case, but you also hinted that maybe one day you'll be able to incorporate it. But I just wanted to ask if there's any relation at all to what Meinhardt and Reinecker and Davison and Meinhardt do in the Calabi-Yau 3 case using intersection cohomology?
I don't know. Well, somehow in the Calabi-Yau threefold case, what you want to do is not look at the ordinary homology of the moduli stack. You want to look at something like the hypercohomology of a perverse sheaf. And I take it that may be what we're talking about. But I don't know how to put interesting structures such as vertex algebras on the hypercohomology of perverse sheaves. I would want to situate the Calabi-Yau threefold thing on the ordinary homology of the moduli stack, but then I don't know to what extent all of that stuff is relevant. Simon?
Yep. So I had 2 questions. One was just there's some interesting structure on the Hilbert scheme of points on a surface. Does that fit in some way into your picture?
Somewhat indirectly, yes. So it's known, for example, that you can put a vertex algebra structure or various interesting representations on the direct sum of all the homologies of the Hilbert schemes. You can build that out of my picture in a somewhat indirect way. So one problem is that Hilbert schemes are semi-stable moduli spaces, but I put structures on the homology of everything. But the fundamental classes of the Hilbert schemes fit into this picture very nicely because they are semi-stable counting invariants. So yeah, so it's probably, there should be a story there which I haven't explored yet, I think.
But my second question was, you had a formula number 3. You had equation 3, a general formula for your homology in the case of, well, derived category of surfaces or something of that kind. So
Yes.
that was very much like the formula for the, if one was thinking differentiometrically, the formula for the, we must say, the equivariant homology of the space of connections, or more or less the same as the maps into the classifying space.
Yes.
Is that
That's kind of more or less exactly what it is. Well, so if you looked at the homology of the maps from X into BU cross Z, that would give you this, except you should replace the K0 SST of X by K0 XM. So that's something you can always do for any complex manifold. And Jacob's theorem is telling you, well, and so there's, well, you can always form a kind of differential geometric moduli stack, essentially of all connections, or of a kind of completion of all connections. And then you can map the homology of the algebraic moduli stack into the homology of the differential geometric moduli stack. And the homology of the differential geometric moduli stack is the thing you're familiar with, the things that come up when you start thinking about moduli spaces of connections. And Jacob's theorem tells you that in some circumstances, the map from the algebraic moduli, the homology algebraic stack to the homology of the differential geometric moduli stack is an isomorphism in some nice cases, essentially.
Supposing you took any space X, then you can look at this maps into the classifying space. Can you define this structure on that thing?
Well, yes. Well, if you take any compact manifold with a real elliptic operator, then I can define the structure of vertex algebra on the homology of the mapping space from your manifold into BU cross Z, which is roughly what you're looking at in equation 3.
Well, perhaps that elliptic operator could be formulated as just as something like a K-theory homology class or something more abstract. It's probably not the actual details of the operator that you're using.
Yeah, you only care about the symbol. So something in the world of a T.S. Singer would be what.
Mm-hmm. Thank you.
Are there other questions or comments? I'll just remind people that you can lower your hand if you don't have a question. There's a. Okay. Well, thank you.